Hello and welcome to Chemical Interactions for Year 8 with Mrs. Castanera. Today we are going to be looking at Lesson 7, what is a mixture and how can we separate one? So today's lesson is titled Mixtures. Our key words, which we'll need to know and understand by the end of the lesson, are solute, solvent, solution, dissolve, soluble, insoluble, ions, saturated. You're already familiar with some of these keywords already. Now I want you to pause the video and complete the knowledge check, please. So we'll just go through the knowledge check answers now. Number 1, give the name for the electrons in the outer shell. Valence electrons. Number 2, give the name for the dome shape caused by the surface tension in water. That is the meniscus. Explain why water is polar. That's because it has a positive and a negative charged end. Explain why some substances are insoluble. Well, they don't have any charged parts. Name the force between water molecules. That would be intermolecular force. Name the bond between hydrogen and oxygen atoms. Hydrogen and oxygen would be covalently bonded, so that is a covalent bond. Give the name of the solid that dissolves into a liquid. That would be a solute. And the reasoning behind that is a solvent, which is the liquid, plus a solute, which is the solid that dissolves into the liquid, produce, when combined, a solution. Name the type of bonding found in salts. That would be ionic bonding. Okay, give yourself a mark out of 8. If you got 5 or more, then good. If less, then you need to review your knowledge organiser. Thank you. So today we are going to be able to, by the end of the lesson, define a mixture, describe the process of chromatography, and calculate RF values. Now, calculating RF values can be quite tricky. This is very high level. We're going to have a go at it so it's at least familiar to us. Mixtures. Mixtures are made of more than one different type of substance. They're in the same space, but they are not chemically bonded together. Therefore, mixtures can be separated more easily than a compound. Some mixtures are very difficult to separate, others are much easier. We use different techniques depending on the atoms or molecules they are made from. If a solute does not dissolve in water, we can use a different solvent, such as ethanol, instead. There are many different types of solvent. I'm going to make some notes here. Make sure you're doing the notes too. So there are many solvents. And you find them, for example, oil. Oil is a good solvent. So oil painting, the oil is the solute. Sorry, the oil is the solvent and the dried paint powder is the solute. And you mix them together and you get an oil and paint solution to make oil paints. And if you ever find you get paint on your hands, for example, if you're decorating at home, then you can use something to dissolve the paint, often called white spirit. And these work by being attracted to different parts of the molecules that they are dissolving. So water is attracted to or whatever it is you're dissolving. So it could be the salt, the sugar, anything that's being dissolved in the water, and the oil is attracted to something in the paint that allows it to be dissolved in it. The white spirit is attracted to something in the paint that allows the paint to be dissolved in it. Okay, so examples of everyday mixtures. So there's a variety of everyday mixtures, including pen ink. So all these inks we are writing and drawing with, they have different colours of ink inside them. So to make different coloured ink, companies will blend different mixtures of various colours. Some inks can have their colours separated by a process called chromatography. Okay, so chroma is the Greek for colour, graphia is the Greek for writing. So you can separate these colours by a process called chromatography. And we'll talk more about this during the lesson. Blood. Blood is in fact a mixture of water, cells and molecules. Now, you can separate your contents of your blood depending on their mass, and this process is called centrifugation. Okay, and what centrifugation is there is a machine called a centrifuge, and it essentially, you can put in small containers, a bit like test tubes, containing samples of blood, and it will spin the blood, the test tubes even, many times per second in a circle. A bit like if you had a yo-yo and held onto the end of the string and whirled that yo-yo round and round, maybe above your head or to the side. And what happens is the heavier parts are forced to the outside of that circle, so to the bottom of the container, because gravity pushes them further down and away from the centre of the circle. So we're going to add a little note about this. So the mixture is spun. In a circle many times per second. Could be hundreds, could be thousands. And so the heavier parts sink to the bottom. And that's because of gravity. Okay, we're going to go on to the next page now, please. Okay, a third mixture is rock salt. Rock salt is used to grip the roads when it is icy. The salt lowers the melting point of the water, which prevents it freezing. And the sand or rock is used for grip. So rock salt is a mixture of salt and sand and rock. So it's a mixture of these 2 or 3 components. Okay, so it can be separated by a process of dissolving and filtering. I'm going to learn more about that in a couple of minutes. Now, we now have an activity that obviously we can't do because we're not in the lab, and I can't demonstrate it because I don't have the equipment at home. So this is all about separating inks or dyes or paints by a process known as chromatography. Okay, so chromatography is a process used to separate different colours that make some inks, dyes or paints. Each ink of the mixture can dissolve in water in a different way. Some are more soluble than others. So dissolve in water, but some are more soluble than others. We can use chromatography paper, which is a special kind of paper, to help separate the inks based on how soluble they are in the solvent and how attracted they are to the paper. So we use this special chromatography paper, and it separates the inks based on how soluble they are in the solvent and how attracted they are to the paper. The finished sample is called a chromatogram. And that is this piece of paper here, which is currently sat in the solution or the solvent. And once it's all dried and finished, that is a chromatogram. But it's not a chromatogram until it's completely done and dry. So the theory behind chromatography. There are two phases to chromatography. There's the mobile phase, which is when the molecules are moving in the solvent. And there is the stationary phase, which is when the molecules do not move and they're stuck in the paper where they ended up. And as you can see by this diagram, we have graded 3 different spots of ink, so ink A, ink B, and ink C. Now this isn't in colour, so we can't tell what colours these were originally, but chromatograms do not deal with black and white usually, they deal with coloured inks. And so the different colours in the ink, so here we have 2 different colour spots that have travelled up from A along with the solvent. So the paper's dipped in the solvent. And if you've ever dipped paper in water, and you can try this at home if you like, with a piece of kitchen roll perhaps, you will find that the water soaks up the paper gradually. And in fact, you might also be able to see at home, if you were to take a piece of paper towel, kitchen roll, put a spot of ink on it, preferably something like a blue or a purple, or brown is often the best colour for this, because brown is made up of lots of coloured inks. Then the different colours will move up the paper, or the paper towel, which is similar, and separating as they go. And so something else similar has happened to B, but there's only one colour in it. And in C, it's also got 2 colours, but they've travelled further. And the reason for that is because those inks were more soluble. So the further they travel, the more soluble the inks are. So let's go through this. Allowing the molecules to move through paper will cause them to move different distances, therefore separating them. Once the process has stopped, we can measure how far they have travelled compared to the solvent. So you can measure how far the solvent travelled, which on this one was here, and how far your various inks have travelled. And this is used to produce a number called the RF value. Now, those inks that travelled furthest along the paper were more soluble than those that travelled the least. So we're going to label this more soluble because it travelled further. And this is less soluble ink. Okay. Now it says your teacher will demonstrate how to perform chromatography. I'm not going to do that. We're actually going to watch a video. Now, what I'd like you to do during the video is use your notes page, so page 37, okay, Lesson 7 student notes page, to make a couple of notes on the video. You don't need a lot of detail, but anything you think is important or will help you to understand the topic more. And then once we've done that, we're going to come back to RF values and have a look at that. So you search for Cognito YouTube, and you can do it on the YouTube website, or you can do it through Google, it doesn't matter. So if you go to their channel, and so once you've got their channel up, you can click on the playlists, and you want to get up the chemistry playlist, and you need to go down the videos, and they're all numbered, and we are looking for the paper chromatography video, so video 48, paper chromatography, and you will need to watch all of that, please. Okay, once you've completed watching the video, please return to the book. So, as you saw in the video online, calculating the RF value is all about identifying how far different parts of the chromatogram have travelled. Okay, so we're going to read through this. RF values. Once the process is complete, you will then have to calculate the RF value of one of the inks using the method below. From the example in the diagram, we can see that sample A is made from 2 different inks, which we can see there's 2 different inks in A. Sample B is a pure substance made from only one colour, and we can see that too. Okay, so it's only got the one colour here, sample B. And sample C is also made from 2 different inks. So there's sample C, and it's 2 different inks it's made from, which have travelled much further than the inks from A. You can also see that A and C have one ink in common, and that is this ink here. So it's likely to be the same ink because they have travelled the same distance. So to calculate the RF of the ink in B, so we're doing B, which is the middle one, we're going to measure the distance in millimetres that the solvent moved from the pencil line to the grey line at the top. So you will take your ruler, for example, and use it to measure this distance. So from the pencil line, which is here, all the way up to the solvent line, which is here. And so for us, that distance on my paper is 3.9. So 39 millimetres, 3.9 centimetres, but we're doing it in millimetres, so it's 39 millimetres. Okay, so for this one, it would be 39 millimetres. Now, next we're going to measure the distance in millimetres that the sample of ink moved, measured to the centre of the spot. So we can do that too. Now, in real life, your chromatograms are likely to be much bigger than this, which will help you to make better, accurate measurements. So that would be 0.9 centimetres, which is 9 millimetres. So our ink travelled 9 millimetres, but our solvent travelled 39 millimetres. And what we can do is we put them into our equation. So RF is going to be distance travelled by the ink. Okay, so the ink only travelled 9 millimetres, divided by the distance travelled by the solvent. Well, our solvent travelled 39 millimetres. And you will, of course, need a calculator to calculate this. Okay, so I want you to pause the video and calculate that, please. So you should have an answer of 0.23, and then it's 07, but the best way to do that is going to be round that to 1. So 231, or just 0.23. Okay, so tick that if you got that correct. If you got it wrong, make sure that you check your calculations. Feel free to use a calculator. Okay, so we're going to move on to the next page. So we won't be calculating an RF value for one of our inks because we haven't done the experiment. However, we will be doing this next activity. So calculating RF values. So we're going to use the diagram and the information below to calculate the RF values of the various inks. Now, helpfully for us, the same diagram as the previous page. We're going to distance the solvent travelled was 80 millimetres, so they've told us that. And then we've got the distance moved by the individual spots. So the two different spots for A, so that's 12 and 46 millimetres. The spot for B, that's 19 millimetres. Just move that up a little bit. The spots for C at 46 and 68 millimetres. So what I want us to do is we're going to do the first one together, and then I'll let you pause the video and do the rest yourself. And you might need to use the student notes page or spare piece of paper if you need more room, that's fine. So to calculate it, the RF value equals distance travelled by the ink divided by the distance travelled by the solvent. And yes, I'm having to write very small here, but you don't need to write all of this out as long as you write out what I'm doing next. So the distance travelled by our ink was 12 millimetres. I'm going to divide that by the 80 millimetres the solvent travelled, and that's going to be the same for all of them. So it's always going to be this number divided by the 80, and 12 divided by 80 is 0.15. And there's no units on this because this is a ratio, okay? So there's no units required for this one. So if what I'd like you to do now is pause the video and continue through these and complete them, getting an answer for each, using the notes page for more space if required. Okay, let's go through those. So the first one for A, as we calculated earlier, was 0.15. The second one for A is 0.575, but I'd like us to round that to 0.58. If you've written 0.575, you're not wrong, that's fine. B was 0.2375, so 0.24. Again, if you've written 0.2375, you're not wrong. C, also at 46, was 0.58 again, which would have been 0.575 on your calculator. And C is 0.85, which claims it comes out at 0.85 on the calculator as well. So give yourself a mark out of 4 for those, please. If you have got 2 or less correct, and it's not just simple rounding errors, then you need to have another go at this, please. Once you've done that, I'd like you to carry on answering the questions for the rest of this page, and they continue on to the next page. Now, question 6, part of the question's been missed off for some reason. My apologies for that. So we're going to finish off that question first. So state the sample with the least soluble ink. So that was state the sample with the least soluble ink. Okay, so complete all the questions 1 to 7, and then we'll come through and mark them together. So, question 1, state the sample that is a pure substance. That is sample B, and the reason for that is there is only one spot. So only one ink spot. It doesn't have 2 like A and C. State the 2 samples that have an identical ink. Well, A and C contain identical ink, okay, and that's because they have a spot that moved the same distance. Okay, state the sample with the most soluble inks. That was sample C. It's the answer to that, sorry, the justification for that, is that it travelled furthest up the paper. So that's the ink spot, travelled furthest up the paper. And then moving on to our next page, state the sample with the least soluble ink. Well, that was A. And the reason for that is essentially the opposite of the previous region. So it travelled the shortest distance up the paper. Okay, so what I'd like you to do now is pause the video and complete the knowledge and application check questions, all 11 of them, and the extension activity, please. So there are 12 questions in total. So we're going to go through those answers now. Mixtures are made of different types of substance. Elements are made of all the same type of atom. The 2 phases of chromatography are the mobile phase and the stationary phase. Give 3 examples of everyday mixtures. Okay, so there's a lot of answers I can accept here. So anything along the lines of inks, dyes, blood is another example we had. Rock salt, these were 3 examples we had in this lesson. There are a lot of other answers you can give. If you have any questions about this, ask an adult at home or email me. That's not a problem to check. But anything that has more than one different material or substance mixed up but not chemically attached to each other. So if you mix sugar and salt, for instance, by accidentally pouring salt into the sugar jar or vice versa, that would be a mix. A substance that dissolved in a solvent is called the solute. What does a small RF value mean about the solubility of an ink? It is a low solubility, as in it's not very soluble. How many spots would a pure substance make? Well, just the one. Why is pencil used to draw the baseline? Well, there's two reasons. Essentially, the main, it's all one reason really. It's insoluble is the reason. If you didn't specify insoluble, you could say it won't move like the ink does, or it's not ink, but essentially the answer is insoluble. Okay, so it's insoluble in water. So it won't dissolve, so it can't move. Explain how we could use chromatography in forensics to match ink found at a crime scene to that ink found on a suspect. So you need to do a chromatogram and compare the ink on the suspect to the ink at the crime scene. There we go. Question 10. A sample of sugar coating on some sweets was sent to a laboratory to investigate how many different dyes were used to make the coating, as well as if any of them were banned from use. The sample produced 3 spots at 3 different distances from the baseline. The solvent travelled 15.7 centimetres. Calculate the RF value of each dye. Now, you may have used the notes page for this, that's fine, but essentially you'll have to do each of those distances. So 3.5 is the shortest distance travelled by the spot, divided by the solvent's distance, which was 15.7, which gives us 0.22. We're going to do 8 centimetres divided by 15.7, which is the distance the solvent travelled, which gives us 0.5, it's 0.9, whatever, but we're going to round that to 0.51. And then the last one was a travelled distance of 13.2, and then it was 15.7, and that gives us a value of 0.84. Okay, so there's a mark for each of these. Question 11. From question 2, explain how the company could check to see if one of the dyes belonged to a banned group of food pigments. So they need to do the same chromatography test on the banned pigments. If the distance is the same, then it's a banned substance. And the extension activity, explain why using different solvents, such as water and ethanol, would produce different RF values even if you used exactly the same samples. So different solvents will move different distances along the paper, which means that the value on the bottom of our equations, such as the 15.7 here, is going to change for every solvent. Every solvent will have a different distance. So there are 12 questions, but question 10 is worth 3. So that's a total of 15. Now, if you got 6 or less, I strongly recommend you review the lesson again and try these questions again. If you got 12 or more, well done. You've done exceptionally well on this. It's very tricky. You've obviously got a handle on the maths as well. So well done. And that is the end of the lesson. Thank you very much.